Hello everybody. So in this video we're going to be talking about section 1.2, which just deals with the basic concepts in differential equations. So let's just look at an overview here. We're going to talk about what is a differential equation, what is the order of a differential equation, and how do we verify that something is a solution to a differential equation. And these are the three things we're going to talk about in this video. So there is one other thing here that we're going to say I'm saving for a later video, and that is actually finding some solutions of differential equations. I'm going to save that for a later video. Okay. So, but let's start with this. What is a differential equation? Okay. So a differential equation is an equation involving the derivative of some function, and we're interested in talking about that function. But all the equation deals with is, what the equation doesn't tell us exactly what that function is, but it does explain how its derivative is related to other things. So that's what we're going to be dealing with. So let me write down some basic examples here. So one basic example might be to say that the derivative of a function y, so dy dx, is equal to a multiple, some multiple k, some constant k times y. So dy dx equals k times y. This is a differential equation. We have the derivative of the function, and we have an equation relating that to other stuff. All right. We might be interested in, what is this function? Or another way to write this would be, instead of using this notation, this is called Leibniz notation, we could use the prime notation, which is usually what we're going to use because it's a lot easier to write down primes than Leibniz notation a lot of times. So other way to write this would be y prime in place of dy dx equals k times y. And so what we're saying is that the derivative of the function is proportional to itself. Another differential equation we might look at would be something like xy equals y prime plus y double prime. So here we have a differential equation involving not just the first derivative, but also the second derivative. We could even do something more than that. We could go to the fourth derivative. Now when we start writing fourth derivatives, it starts getting tedious to write down these primes. So what I might do is use Leibniz notation and write d4y dx to the 4. That's the fourth derivative of y with respect to x. And maybe the differential equation is something like this. So here we have the fourth derivative of y with respect to x is equal to x divided by the second derivative plus 3. If we use primes, well, it's a little bit tedious to write 4 primes in a row, so what we do is we'll write Roman numerals. Sometimes people would write it like that. I think it's a nicer way to write it. It's a little bit cleaner than using Leibniz notation. Or, if you don't want to use Roman numerals, usually what we'll do is we'll use just a number. Right? So instead of writing Roman numeral 4, I'll write 4 in parentheses. Now those parentheses are important. If I don't write parentheses, that would be y to the 4th power. But with parentheses, we understand it to mean the 4th derivative. So keep that in mind. If we ever want to denote a derivative, we're going to put parentheses around the number in the exponent, and then we know that we're talking about derivatives here. Okay, so this would be written as, I'm still going to use primes down here. I could write parentheses too, but usually if the derivative is 3 or less, we just use primes. Okay, so that's another way to write. These all are the same differential equation. And so we could even go crazier than that. We could do something like, the y to the 72nd derivative. That's a lot of derivatives, but that's totally cool. And maybe that just equals 0 or something. That's a differential equation. Now, one thing that we can talk about here is the order of these differential equations. The order is a very important thing to keep track of. The order is the highest derivative that appears in the equation. So we just look at all the appearances of our function in the equation. In this case, I was using y to denote our function. And we find out the highest derivative. That's the order. So very simple. Right? So if we look at the first differential equation here that we looked at, what's the highest derivative that appeared? Well, just the first derivative. So this is an example of a first order differential equation. Right? So this is first order. Let's go to the second one. What's the highest derivative that appeared? Well, here we have the 0th derivative, first derivative, second derivative. Second is the highest, so that's an example of a second order differential equation. What about this one? Here we have a fourth derivative, second derivative, and no other derivatives in here. So the highest is fourth. So this is all different ways of writing the same thing. This is fourth order differential equation. And finally, this one, 72nd order. That's a pretty high order for a differential equation, but totally legit. All right, so that's order of differential equations, just the highest derivative that you see. We're going to be looking at differential equations where we can solve for the highest order term. Just differential equations where we can actually solve them and write the highest order term on the left-hand side. Okay, so if it can be solved for the highest order term, like I said, I can write that highest order term. Let's say it's y, the nth derivative of y. If I can solve it, that means I can write it on the left-hand side with an equal sign. And then what's on the right-hand side? Well, it's going to be a bunch of other stuff involving lower order derivatives, and also maybe the variable that the function depends on. Okay, so like we had up here, this was solved for the first order derivative, and it's written in terms of, I will say, x and y. Now, x doesn't appear here, but you can think of this as a function of x and y that just happens to not depend on x. Okay. Here we have a second order derivative, a second order differential equation. I could solve this for y double prime. Right? And if I solve it for y double prime, what will be on the other side of the equation, equal sign, will depend on y prime, x, and y. So when we solve it for the highest order term, what's left over on the other side of the equal sign is all the lower order terms and x. Okay, so what that means is that we can write it like this. We can write it as a function of x and all the lower order derivatives. So all the derivatives up to and including n minus 1. So y double prime and dot 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 all the way up to the n minus first derivative. So on the right hand side we'll have a function of this stuff. Okay, so let's just look again at these examples that we looked through. Y prime equals xy. Well, what does that become? Y prime equals xy. Well, that's the same thing as saying that y prime is a function of x and y. The function of x and y just happens to be xy. Okay. What else can we can look at some of these other examples, like this one over here, the second order differential equation. Let me write that down again. So xy equals y prime plus y double prime. If I solve this for the highest order derivative, that's y double prime. What do I get? I get y double prime equals a function of x, y, and y prime. What is this function of x, y, and y prime? In this case, it's going to be, let's see, if I solve this for y double prime, I get y double prime equals xy minus y prime. So in this case, the function is just xy minus y prime. But I've written y double prime as a function of those three things. And let's just do that one more here. Let's just do this one with the fourth derivative. So I'll write it down like this. All right, so we have the fourth derivative of y equals x over y double prime plus 3. Well, it's already solved for the highest derivative, so I've already written it in the form f of x, y, y prime, y double prime, and y triple prime. It's a function of all of these. It happens to only depend on x and y double prime, but I can think of it as a function of all of these. Right? It just happens to not depend on, for example, x triple prime and x prime. Right? But you can think of it as a function of all of them. And so it just happens to be this function. But we're going to be looking at differential equations where we can write them in this form. I invite you to try to think of differential equations where you won't be able to do this, where you can't solve for the highest order derivative. It's not too difficult to come up with lots of examples where you just can't solve for this. Those are interesting differential equations, but they're just not the type that we're going to be looking at in this class. Okay? So it's not that they're not important, it's just that we just aren't going to be focusing on them. Okay, so finally, I want to talk about that last topic, verifying solutions. How do we verify when something actually solves our differential equation? I mean, that's really what we're interested in this class, is understanding the solutions to a differential equation. All right, so let's look at a basic differential equation here. We'll look at that first one we talked about, y prime equals k times y. Now, what is k here? I should point out that k is a constant. It's not the variable, not that y depends on k. It's just a constant. It's just a number. Okay? And I want to know, if I throw a function at you, you should be able to check to see, does it solve this differential equation? So for instance, is y equals x to the k a solution? That might be a good guess at what the solution might be. So is that guess correct? Y equals x to the k. Well, how would I check it? Well, I just have to plug it in and see if it makes the equation true. It's just like substituting in algebra. So I have to take the derivative to compute what this is. So we compute y prime. If I compute y prime of x to the k, I get k times x to the k minus 1. And then I have to compute k times y. K times y is just k times x to the k. Now, the differential equation says that these two things have to be equal. Are these equal? No, they're not. They're both polynomials, but they're different. They're different polynomials. This one has order k minus 1. This is a polynomial of order of degree k. I should say degree instead of order, since we're using order for differential equations. This is degree k minus 1. This is degree k. They're different polynomials. They only differ by 1 degree, but they're different. So no, that's not a solution to the differential equation. Okay, what about this? Is y equals e to the kx a solution? How about this one? Well, again, I need to check y prime and ky. So let's compute y prime. If I take the derivative of this, I get k times e to the kx. If I compute k times y, I'm just going to multiply this by k. I get k times e to the kx. Now, the differential equation says that these are supposed to be equal. Are they equal? Yeah, they're exactly the same function. Exactly the same function. So yes, it is a solution. Let's do another one. Is y equals c times e to the kx a solution? Now, c, if I don't say otherwise, or if the book never says otherwise, always assume it's a constant. C stands for constant. So it doesn't depend on x, it's just a number. Okay? So is that a solution? Well, what do I have to check? I have to check y prime and k times y, see if they're equal. Y prime, if I take the derivative of this, well, c is a constant, so I just jump past it, take the derivative of this, I get c times k e to the kx. And then I got to check k times y. K times y is equal to k times this, so that's k times c times e to the kx. Are these equal? Yeah. I mean, the c and the k are in different orders, but that's, you know, multiplication's just commutative, right? So yeah, these are the same. So yes. So interesting. You know, we verified that this is the solution, but then we found more, right? So don't fall into the trap that, you know, thinking that you know, once you find a solution that you found all of them. No, there could be more. Differential equations may have more than one solution, so keep that in mind. Okay. And that's it. That's all I have for this video. In the next video following this one, we're going to talk about actually how to find these solutions. How do you actually come up with those guys? All right. But I'll see you in that video. So see you later.